problem number 6, use Maclaurin series to evaluate the limit as x goes to 0 of x minus sine x divided by x times 1 minus cosine of x. So something that we should realize here is that we plug in 0, we would get 0 minus 0, that's 0 upstairs, 0 times 1 minus 1, that's a 0 downstairs. And so this is a 0 over 0 indeterminate form. And so because it's a 0 over 0 indeterminate form, L'Hopital's rule would certainly work here. It would certainly apply, and you get the correct answer. But sometimes that can be a little bit complicated. You might have to do multiple applications of L'Hopital's rule. Also, you're specifically told in this problem to use Maclaurin series. So what we're going to do is that we're going to replace sine x and cosine x with the first several terms of their respective Maclaurin series, and that's going to make our lives a lot easier. So let's jump into this. The limit as x goes to 0 of x minus, so the first several terms of the Maclaurin series of sine x are x minus x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial divided by x times 1 minus cosine x. Cosine, is the Maclaurin series there, is going to be 1 minus x squared divided by 2 factorial plus x to the 4th divided by 4 factorial minus x to the 6th divided by 6 factorial. So parentheses, parentheses, parentheses. Okay, so we replace these with their respective Maclaurin series. Let's see if anything cancels out. Let's see if anything simplifies. So upstairs, we have an x minus x, so we can cancel those out. Downstairs, we have a 1 minus 1, so we can cancel those out. So what happens now? Let's rewrite the numerator and denominator. Let's be careful, though, with distributing out the minus sign. So upstairs, minus times minus is x cubed divided by 3 factorial minus x to the 5th divided by 5 factorial. Downstairs, we have x times, those cancel, and minus times minus x squared over 2 is plus x squared over 2 factorial minus x to the 4th over 4 factorial plus x to the 6th over 6 factorial. Okay, we're making progress here. And one more thing I'm going to do is I'm going to multiply through here. I could multiply through here by x downstairs, but instead I'm going to do something else. I'm going to try to factor things out from the numerator and denominator so I can cancel things. What am I going to factor out? I'm going to factor out as big of a power of x as I can. So upstairs, that's going to be an x cubed. So this is going to be 1 over 3 factorial, so it's 1/6, minus x squared over 5 factorial is 120. And all the other terms would be like x to the 7th, x to the 9th, so that would be like x to the 4th and x to the 6th here. And then downstairs, I'm going to factor out an x squared from these terms here. So x times x squared will give me also an x cubed. So x squared divided by 2 factorial. We pulled out the x squared, so that's just 1/2. We pulled out x squared from here, so that's minus x squared over 4 factorial plus x to the 4th over 6 factorial, 720. And what happens now is those x cubes cancel. So I'm just left with the limit as x goes to 0 of this divided by this. And now, we are finally at a point where it's no longer a 0 over 0 indeterminate form. Because if we plug in 0 upstairs, we get 1/6. This will be 0, and all the other terms have x's in them as well, so those will all be 0. Downstairs we'll have a 1/2 minus 0 plus 0, but these will all be zeros as well. So the only thing that's left the only thing that's going to be left here, so 1/6 minus 0 plus 0, divided by 1/2 minus 0 plus 0, So it just ends up as 1/6 divided by 1/2. So our final answer is 1/3. So this is a useful little reminder that Maclaurin series can be used to evaluate limits without resorting to L'Hopital's rule. You would have had to use L'Hopital's rule several times, at least 3 times, to clear everything out in order to make this work. So this is an alternative way that avoids, taking the derivative x times 1 minus cosine x. You'd have to use the product rule. This kind of avoids a lot of the pitfalls, a lot of the difficult complication with L'Hopital's rule.